So I said I was going to talk about logic, but that's like super vague. So I don't know. What were you guys expecting me to talk about?
Logic.
Cool stuff.
Cool stuff. Yeah. So that's what I was.
You should first explain what logic means.
Well, so that's kind of hard to explain, right?
Yeah.
So logic has kind of been this thing that I guess has been existent for a really, really long time. Like, I guess people attribute it to like Aristotle or whatever. But what Aristotle did isn't even really close to what we've done in the last century or so. And that's more what I'm going to be talking about. So there's this program over the last 150 years or so to sort of ground mathematics in like really basic principles that we all agreed upon. So like if P is Q, if P is true and P implies Q is true, then Q is true, right? It's like super basic. You know, if P is true, then the negation of P cannot be also true. And, you know, you have many things. We actually, sometime in the 1800s, came up with this thing called set theory, which is mostly what I'm going to be focusing on today. So, is it fair to assume everyone knows what a set is? Okay, cool. So when we talk about sets, we usually think that this is really a good place to start because there's somehow this fundamental object. Sets are almost like identical to concepts, right? Like, if you think about a set of things, then that is sort of a description of these things. And if you think of a description of some things, then this forms a set, right? So if I talk about the set of things that are blue, you can say, well, this thing's blue or this thing's not blue, and this forms a set. So Cantor did a lot with this. I don't know if you guys know Cantor, anyone? Okay, well, that's good. Cantor in particular was really interested with infinite sets. So one particular infinite set is like the set of the natural numbers. So just in case I decide to write anything about this, the notation is usually as follows. And you also like to think about the rationals, as many people do. Is this notation fine?
Is it convention to have 0 in the rationals?
Yes, it is definitely convention to have 0 as a member of the... Oh, did you say naturals?
Yeah, naturals.
Oh, yes. So this is like a controversy, supposedly, but 0 is clearly a member of the natural numbers. I will publicly make a statement about this one.
I don't know, I find myself writing in not a lot.
Yeah, let's not discuss this. So, there are lots of ways to define the set of real numbers, but I'm going to leave that to intuition here, because I don't want to describe it. I mean, briefly we can say it's the completion of the rationals. So if you like take the limit of all, like, of any sequence in the rationals, if it has a limit, you get a real number. And this sort of defines the set of real numbers. Okay, so anyway. So some interesting things Cantor thought about were how big these sets are, right? So clearly they're infinite in size, but you might think, well, maybe one's bigger than another, or maybe they're all just the same size, or what does that even mean? So something Cantor thought about was, if I want to count some things, or if I want to tell that two things have the same number of objects, I can just pair the objects up. And if I can put every object from each like party in a pair, then I know that they have the same number of things, right? So for instance, I can tell that there are at least as many chairs as there are people in this room because excluding me, all of you are sitting in chairs, and some chairs don't have people, right? But if every chair was filled and we didn't count me, then I would know that there are the same number of people as there are chairs, right? So we formalize this by saying two sets are the same size if there's a bijective function between them. So a bijective function is just a function that is one-to-one and onto. So real quick, we say A and B are the same cardinality, formal. This basically just means size. If there is a function f, so this just means the function maps members of A to members of B, such that, so f of A equals f of B implies A equals B. So what this says is that there's nothing in B that gets mapped to by two different things, right? If A maps to the same thing as B, then A and B are really the same thing, right? And if we have an element of B, so this says if B is an element of B, then there is some element of A such that f of A equals B. Right? So what this says is that everything in B gets mapped to, and no two things in A get mapped to the same thing. So usually we call this first condition one-to-one, or injectivity, and the second condition is onto, or surjectivity. Is that okay? Great. All right, so now that we have this nice formal definition for two sets being the same size, we can kind of tell that if we have two finite sets, say with 5 elements, there's a clear, easy way to show that they're the same size, right? So if I have 1, 2, 3, 4, 5, and say 2, 4, 6, 8, 10. All right, then the function f of A equals 2A witnesses that these two are really the same size. Great. So now, with this notion in mind, we can kind of answer questions about how big these are. Okay. This is really one of the bigger things that Cantor did. This is actually extremely surprising at the time, the results that we'll get. So I'm going to ask you guys, this is clearly the smallest, right? And this is clearly the biggest because they're subsets of each other. So now I'm going to ask you guys what you think the relationships are between them. All right, is the set of rationals bigger than the set of naturals? All right, probably. Is the set of reals bigger than the set of rationals?
Yes.
All right, also probably. All right. Well, let's tackle these questions. This is probably fine to erase. I assume you guys can remember these symbols. All right. So our first theorem. All right. So when I draw this like modulus sign around a set, that means size of. So the set of the naturals has the same size as the set of rationals. Who knew? Okay. All right, so let's prove this. So what we want to do is construct a function that maps each natural number to a member of the rationals in such a way that no two of these get mapped to the same one, and every one in here gets mapped. Alright, the second condition is really the important one. Clearly, if we had a way to map to all of them, but we accidentally mapped two of them to the same one, we could fix this very easily. So let's focus really on the second part. So how do we do this? You guys have any ideas? Use math. That seems like a good idea.
That might not be very helpful here.
Well, so there are a lot of ways to describe this. I'll do this pictorially. This is the way people usually describe this function. We could actually just write a short arithmetic function, and it would work just fine. But so we can think about the rationals as sort of points on this grid here, right? Where this axis represents the numerator, this axis represents the denominator. Right? So we'll actually have nothing on this axis because we can't have zeros or denominator. But everything else will be fine. Right? And our point's going to form a lattice. You can already kind of see by the way I'm making these dots that there's some sort of ordering on these, right? That this procedure will get every rational number forever. And so that's really exactly what we'll do. Right? So we start by mapping 0 here, and then we map 1 here, 2 here, 3 here, 4 here, 5 here, 6 here, etc. Right? And we can show that this function definitely maps to every single rational number, because if I give you a rational number, you can just look at the numerator and denominator, and you take the maximum and then square it, and that's like roughly the number of steps it'll take to hit it in this procedure, right? So are we all okay with this? Can anyone think of a maybe more elegant way to write this? Well, that's okay. You guys can think about it. Okay, so we've proven that the rationals and the natural numbers are the same size. That is, that we have just as many of these as we do of these, which should be really strange. It should feel uncomfortable because, this is a subset of this, and there are infinitely many of these in between each of these, right? That's perhaps the most uncomfortable part about it. So, when we draw our number line, right, we have 0, 1, and we have an infinity of rationals in here. But somehow we managed to kind of put them all in this pairing, and it works out really nicely. Okay, so perhaps the more shocking result of Cantor, which is probably maybe the more intuitive result somehow, is that we really have more real numbers than we have natural numbers. So a more famous theorem by Cantor is that we have more real numbers than we do natural numbers. Okay, so this was easy to prove because all we had to do was give this function, right? But here we have to really show that there's no such function. Right, so this, you can imagine, might be a lot harder. We have to show that no matter what function I give you, it can't possibly be a one-to-one onto function from this set to this set. Yeah? Alright, so how do we want to prove this? Maybe we could use one of the proof techniques Peter talked about last week.
Proof by contradiction.
Yeah, proof by contradiction. So what are we assuming then? We assume that they're the same size, and then we say because they're the same size, that means there has to be some bijection, right? So really what we're assuming is that we have at least as many naturals, right? Or that it's not strictly less than, but it's easy enough to show that, for every natural number there is a real number. So we can go ahead and eliminate the case where this is strictly smaller. So we get that the number of naturals is really identical to the number of reals. Okay. So because of this, there is some f from the naturals to the reals, such that f is 1 to 1 and onto. Right? So we could describe this function as kind of an infinite list, right? So it's an infinite list starting at 0, then 1, then 2, and it just kind of lists all all the real numbers. So let's write our hypothetical list. And as an example of maybe how powerful this statement is, we're actually going to assume that the real numbers are really just between 0 and 1. We're not even going to, we're going to assume that we just have this, and then we'll show we can't even do that. Right? So our list is kind of like 0 maps to something, 1 maps to something, 2 maps to something, etc. And we might get like 0.5239 4. So this is just a hypothetical list. Of course, we in no way are assuming that these are actually the numbers we're mapping to, although we could. So what am I going to do here to show that this list can't exist? I want to give you a real number that can't be in this list. A real number in our interval that we set this map to, right? So we said this is really a list of all numbers from 0 to 1. And I'll show you that we had to miss something. So how do I do that? Well, I want to make a number that's different from every element of the list, right?
You just have to can extend the decimal expansion.
What do you mean?
Go further in your decimals.
I don't follow.
I mean, you have to cut off at some point in your decimal expansion.
Do I?
You don't have
I mean, you're right, I can't write the number down forever, but that doesn't mean I can't map to it, does it? Certainly I can construct functions from naturals to irrational numbers that I can't write down.
Yeah, if you could just like having like one of your numbers could map to like 1/5.
Yeah. Right, so what I want to do is I want to give you a way to make a new real number out of all these real numbers, but it has to somehow be one that should be in the list. Right, so one way to do this is to just start by saying, well, let's make sure the number doesn't have a 5 here. Okay? So maybe we'll define our new number as x. It'll be 0. Well, if we have a 5, let's just make it a 0. Alright, when we see 6, let's make that a 0 too. We see a 0, let's make that a 1. Now anytime we see something that's not 0, let's make it a 0. Anytime we see something that is 0, let's make it a 1. Is that okay? Alright, so just make sure this is completely clear. Right, we look at this. Well, it's not a 0, so we make it 0 here. Alright, so we've defined a real number, x, that has to be different from every number in this list, right? Alright, suppose x is the same as one of the numbers in the list. Well, then it's the nth number in the list, right? Well, then we just go to the nth decimal place, and we see that they disagree at that place. So then it can't be in this list. But surely this number is at least 0 and at most 1. So it has to be in the list. So this is a contradiction. Right? Does this make any of you guys uncomfortable? I feel like this should make you uncomfortable. This should be really exciting. To like deal with infinity head on. So yeah, this was like insanity, I think, to Cantor. He was like, how could this possibly be? What does this even mean? And then, of course, he went insane, like actually.
Oh.
Yeah, he died in an asylum.
Yeah.
Was he doing that?
Probably not.
So, he wasn't doing much math when he was imprisoned or asylumized. What do you call it when you put someone?
Institutionalized.
Institutionalized. There you go. Thank you.
Sounds so nice.
Yeah. So Cantor actually generalized this result, and he showed something a lot more powerful. This will be our final result due to Cantor. I suppose I need to define something before I state this. Alright, so definition. We're going to define the power set here. So P of A is the power set of A. Alright, and the power set is just the set of all subsets. So power set of A. It's just the set of all S, so that S is a subset of A. Alright. So what subset means is that it's a set, and every single element in S is also in A. Is that okay? So just some quick examples. The sets of 0 and 1 is a subset of the set of 0 and 1. The set of 0 is also a subset of the set of 0 and 1. Alright, the set of 0 and 2 is not a subset of the set of 0 and 1. Alright, we also have the empty set. So the set with no elements is a subset of 0 and 1. Now, I'm sure this is hard to see, but it's not actually that important. Alright, so we actually listed most of the subsets of this. I missed one of them, just the set of 1. Right? So is this notion clear? Yeah.
If you switch it to 1, 0, is it?
Oh,
Does it matter?
right. So maybe I got ahead of myself. I should have defined sets a little more rigorously. So two sets are the same set if they have the exact same set of elements. If every element in one is in the other and vice versa. So the set of 2 and 1 is the same as the set of 1 and 2. Because whenever I find an element in one of them, it's in the other. And I can't find, so every element of A is an element of B. And if I find every element of B is an element of A. That's a loser. It's almost like, it feels like too basic a notion to even describe. So yeah. So then I'll say the theorem that Cantor gets out of this. He says, the size of A is strictly less than the size of the power set of A for all sets A. Alright, so he says that if I give you a set and then take the power set of it, the power set has to be bigger. Okay, so let's prove this. How do we want to prove it? You guys have any ideas?
Contradiction.
Contradiction. Awesome. Alright, so suppose they're the same size. Right. Well, we can actually do something, we could do something really similar to what we did before if we were talking about the naturals. We could sort of make this list, but for all we know, A might be something bigger than the naturals, it might be the reals, and then we actually showed we can't make a list of the reals, right? I don't have any nice way of writing a list of the reals on the board, so that doesn't help. This still gives us a function. There exists a function f, such that f maps A to the power set of A, and it's 1-to-1 and onto. Right? So is this clear? Which is assuming we take every element of A and we pair it with some subset of A. Okay? So we have this bijection, and what we want to show is that there's actually some member of here that didn't get mapped to. Right? So we have a really clever way of devising this, but I'll give you guys a chance to think about it for a minute if you guys want. Anyone have any ideas? Have you guys ever heard of the liar's paradox? So it's like it's sort of this statement like, it says this sentence is false, right? Perhaps I should have opened with that. That's a really good topic for logic, right? This statement sort of introduces the fact that self-reference is like the enemy of all reason. But it's like so powerful. We use it in mathematics all the time. I imagine you guys use it in physics somehow. I don't know. I'll use it in computing a lot, obviously. So yeah. So we want to look at an element of here that somehow is like the liar's paradox for this F. Alright? So we can look at a set in here that sort of makes F kind of be like, what's going on? You know, what are you doing to my head? Kind of like this liar's paradox. Okay, so the same way we have kind of true and false, we want to put labels on F mapping things to sets. So we want to say, so the way it was taught this, we call sets good and bad, and so that's what I'm going to do because that's somehow the easiest way for me to remember how to do this. So we say an element of A is good if it's an element of what it maps to. Alright? So every element in here gets mapped to some set. Alright? And then that element's either in that set or it's not in that set. Right? So we say it's good if the set it gets mapped to contains it. For instance, if we have f of 0 is the set of 0 and 1, then we get that 0 is good. Alright? But if we have, say, f of 1 maps to the empty set, then we get that 1 is not good. Right? Because the empty set doesn't contain 1. Alright? Yeah.
How, I know nothing. How is the right side, like when you say f of 0 equals the set of 0 and 1, what selected that? Is that the first set in the power set?
Oh, no. This is some arbitrary function. I'm just saying, suppose this is true, then this would mean 0 is good. This is just, I'm pretending this is the function. I decided this arbitrarily.
Okay.
And we want to show that, in fact, no matter what this function is, it's going to mess something up. So we don't get to assume anything about, mapping 0 to 0 and 1. In fact, we don't even get to assume A has 0, right? I suppose we could make some generalizations that let us assume that. But... Alright. So there is a subset of A that's the set of good elements, right? So we can talk about all the elements that get mapped to sets containing themselves. There's also a set of elements that aren't good. So maybe we should look at this one. I think this is the right one to look at. So consider B, which is a subset of A, to be the set of bad elements, or elements that are not good. Right? So now we're going to ask the question, what maps to B? Is that okay? So F was onto, so something has to map to B. So what element of A maps to B? So let's think about this for a second. All right. So suppose this element exists and it does map to B. All right. Well, there are two options for what B could be. Either it's a good element or a bad element. So suppose B is good. All right. So can somebody kind of explain to me why this is not good? Or is it good? Yeah. That's exactly what it is. Right. So so he said this is Russell's paradox, isn't it? Oh, we'll actually talk about that in a minute. So yeah. So what happens is that we suppose B is good. Well, then by definition, B is an element of f of B. Right? That's just exactly the definition of good. But B is the set of bad elements. So this is a contradiction. Right? So then B must be not good or bad. So B is bad. Alright? But B is bad. So B is in B. And then again we have a contradiction because that would make B good. Alright? So now we've successfully shown that when you take the power set of a set, you get a bigger set. So now let's explore some consequences of this. Alright? So suppose I give you an infinite set, like the natural numbers, and I take the power set. I get a bigger set. I take the power set of that, I get a bigger set still. In fact, I can do this ad infinitum, and this tells me that I have infinitely many different infinite sizes of sets. Right. So, is that like mind-blowing? Right. So this is really the body of Cantor's work that's understandable in a 50-minute lecture, I think, or an hour lecture, however long this is. He did have other work. I think he worked in analysis for a bit, but this is really... He founded set theory, and he did a lot with it. He did a lot more work than just this in set theory, too. But I want to visit kind of how he made set theory, right? So he kind of built set theory on this premise that sets really are just concepts, right? So if I give you some sort of notion, a description, then you have a set of things that fit that description. So if I talk about the set of things that are odd, or if I talk about things that are odd, I have a set of things that are odd. Because everything's odd or it's not odd. Right? If I talk about people, I have a set of things that are people and a set of things that are not people. As long as we have a rigorous enough description of what people is. As long as we can look at something and evaluate whether or not it's a person. Same with real numbers, right? We have the set of real numbers, so we have things that are real numbers, things that are not. And so what Cantor said is, as long as we have a description like this, as long as we have a statement such that, like if I have a sentence with a variable x, so we might write this as kind of q of x. This is a sentence with a variable x. As long as it's always true, as long as it's true whenever you plug in x, or false whenever you plug in x, it defines a set. Right? And this seems pretty reasonable, right? Right? And the other stipulation he has is that two sets are the same thing if all their elements are the same. Right? So as long as I don't have elements in one that aren't in the other, then I'm good. But later on, like 30 years later, I guess 30 years after Cantor built this beautiful body of work, we find out that this is terrible. Somehow this really simple notion blows up in our face. And like Gilly said, this is actually because of Bertrand Russell. I mean, it's not because of Bertrand Russell. Bertrand Russell is the reason we know about it. Other people found other contradictions but that Bertrand Russell didn't find, so it's quite clear pretty quickly once you find a contradiction, you can find a whole mess of them. So what Bertrand Russell found was what we call the Russell set. Right? So we define the Russell set as a set of sets such that the set is not an element of itself. Right? So clearly, our Q of x in this case is, we can say Q of x is the statement, says x is not an element of x. Right? And clearly we can evaluate this, right? For everything, we know that that thing is either an element of itself or it's not. So this statement will be true or false given any x.
Can you give an example where it's not an element of itself? Like, what is that?
Oh yeah. So the empty set has no elements, so the empty set's definitely not an element of itself. Something that is an element of itself, well, it's really hard to I mean, there are problems with having things that are elements of themselves because we can't write them in a nice way. So this is a set that does have itself as an element because we named it and then we wrote it here. But if you wanted to write it without this name, you'd have to sort of write infinitely. So most of the sets, like the set of naturals is not an element of itself. The set of reals is not an element of itself, right? Okay. So this seems really nice, right? Like, a set of things that aren't elements of themselves are most things we look at. But it turns out this is a horrible notion just like this was, right? So we look at R and we say, is R an element of itself? You know, is the Russell set an element of the Russell set? Well, suppose it's not. Okay? Well, then it contains a set of exactly those things that are not elements of themselves. So it has to be in the set, and that's a contradiction. Alright? Well, let's suppose it is an element of itself. Well, but then it has something in it that contains itself, and again, it violates the description. So it shows that within Cantors Theory, we can't have this set, but we have to be able to have this set based on how we wrote this. And this is not the only hole we have. I mean, like anything that has this is a substance bad. If we think of the set of all sets, right? Something even nicer. We have just let our Q of x be x equals x. Things that are themselves, right? That's everything. This set's bad too, alright? And that's maybe even more alarming. And there are many reasons why this one's bad. So the biggest reason I think of, or I think maybe the most intuitive reason why this one's bad is because if you think of the set that has everything, then it's the biggest set, right? Because everything else is a subset of it, so it can't be bigger, right? If I have, maybe we say T is a set of sets such that they are themselves, well then, if I consider just an arbitrary set A, it has to be a subset of T, because everything in A is itself, so it has to be in here. Yeah? Right? And so this gives us that T is at least as big as A. Alright? But what if we look at the power set of T? Well, this has to be bigger than T, but this is a problem too. So, whole mess of contradictions in this theory. And I think Bertrand Russell was regretful when he discovered this. Yeah.
So why aren't we able to make a mathematical basis of being like, whenever we need to define a set, be like, let this be the set of all sets that are not paradoxical, and would lead to something like this? Why is it a problem that there does exist a set that could be constructed that is paradoxical?
So you're asking, why can't we just restrict ourselves to sets that aren't like somehow contradictions?
Yeah, well, I mean, if I'm getting you right, you're saying that the mere existence of that set, the set of all sets that don't contain themselves, breaks set theory.
Yeah, it certainly breaks Cantors set theory.
So
But-
why does that have to break set theory? Do we have to explicitly use that to do anything?
So Cantor just postulated these two statements about set theory. He said that if I have a description, I have a set of things that fit that description. And he says two sets are the same under these conditions we've described. And just given those statements, we get a contradiction. So to have a set theory, we really have to define it some other way. And we do that. We have, I'll talk about this very briefly. We have something we call ZFC. So it's like Zermelo-Frankel set theory with the axiom of choice. And this is an axiomatization of set theory. It actually is an infinite number of axioms, much more complicated than this. But people think it works. And I'll actually talk for a minute about why we can't know that it works. Or actually, maybe I don't even have enough time for that. Well, let's actually, yeah, we can just go into this. So Bertrand Russell came up with this thing, Ferg set theory. Many other people did the same thing. Everyone that worked on this was in tears. It was a crisis of mathematics. Solidly, I think 10 or 20 people had their lives ruined. And Bertrand Russell, to his credit, tried to fix it. I don't know if you guys have heard of this Principia Mathematica. Right, it's extremely long text that Bertrand Russell and Alfred North Whitehead tried to make to fix their destruction of mathematics. I can't talk too much about this because I don't know enough about it because, as I'll tell you in a minute, it also had its problems, so people won't use it. But also it's like super, super terse. It's a very, very, very terse axiomatization of mathematics. It takes them a very long time to prove anything. It's very symbolic, which is, I'm sure, beautiful, but unreadable. So what happened when they did this, when they made their system, there was this other guy, Kurt Gödel. I'm sure some of you guys have heard of him. He broke their system. So he, in fact, showed that if you have any system of mathematics that's capable of describing arithmetic, so statements that are true about natural numbers, then it turns out that you have these holes in your theory. You have things that you can't prove, and, well, things that you can't prove unless your theory is inconsistent, which means that you can prove whatever you want, which is useless. So I'll talk about this maybe for a minute. So are we all on the same page when I say like system of mathematics? Like a formal system is just, it's kind of a list of basic true statements as well as rules for deriving new true statements. So fundamentally that's what we're always working with that in kind of the back of our heads. We always have some rules for how we derive new true statements from previously known true statements. And we have some really basic assumed true statements as well as the body of things that we know people have proven from them. And what Kurt Gödel shows is that as long as your system can talk about natural numbers in a way that can describe the true statements about natural numbers, then your system can't possibly be able to prove all of its true statements. There will be true statements in your system that have no proofs.
That are axioms?
That are not axioms, yeah. So we can think of axioms as having proofs in a sort of trivial sense, like they have very, very short proofs, and that's just stating the axiom. So we really mean statements that no matter how hard you try, you can't start from the axioms and arrive. You cannot conclude this statement. And this was also terrifying to solid 10 or 20 people. I would like to think it was terrifying to like all mathematicians. But I really don't think that many people appreciate it well enough. Yeah.
Can you make those unprovable theorems axioms as well?
So yeah. So let's talk about that. So it turns out that if you make them axioms, you just get new unprovable statements. And you could keep trying for a really long time, and you'll never get all of them, unless you have infinitely many axioms. But then I think you still run into problems.
Take the power set of your axioms.
Well, okay, so let's not go there. We don't want to talk about having uncountably many axioms because we really want to be able to write down all of our. We want to be able to at least describe like how a computer might write them down or something. Yeah.
I think this is appropriate and useful to ask, but can you explain like complete systems? Like for example, can you explain why geometry is very good?
Sure.
As
So-
like axiomization of geometry, why that is like an ideal thing to go for.
So maybe I slipped up by not grounding this
Rigor.
in a background, such that this is useful. But so you guys have all heard of David Hilbert, right? Because you guys take quantum mechanics classes and they use Hilbert spaces. And I don't think I have any other basis for assuming you would have heard of David Hilbert. But Hilbert was like the leader of all mathematicians in the 1900s. He was like math king. Everyone listened to him, except for the rebels that hated set theory. But he was like, we're gonna make this set theory thing work. And more to the point, we're gonna do everything. We're gonna do everything because mathematicians can do whatever we want. He laid out this beautiful set of problems, and he's like, we're all going to solve all of these problems, because every problem can be solved if you try hard enough. And then Kurt Gödel was like, actually, no. That's not true at all. Most problems you can't solve. When he laid out this program, people sort of got this, they had these really strong notions that they were looking for. So when they talked about mathematical systems, they were talking about proofs that could be generated in a completely rigorous way, right? So the easiest way to describe it nowadays is just saying a computer could read it. But the proof has to be finite, and it has to use symbols that you've allowed yourself, which is very easy to deal with. And it has to operate on a very strict set of rules. And, I mean, this is, of course, this conforms with the notion of proof we have. It's just we're lazy. So we call this, so we say a system is complete if for every true statement of that system you can derive it from the axioms and the rules, right? And for simple systems, this makes complete and total sense because you can think of the true statements as just the derivable ones, so it's not interesting. But for other systems, you know, we know things like every statement P, right? Statement P is true or false, right? So this is interesting because that says that if we write down a well-formed sentence in our system, then we either have P is true or we have not P is true. Means not, or the negation, right? So this is how we really can get to this point where completeness is actually interesting, because I can make a statement of mathematics as long as it fits the language I've allowed myself and the construction of my sentences, and then I know either that sentence is true or saying it's false is true. One of them has to be true. And so we call a system complete then if for every statement P, you can say P is true, you can prove that P is true, or you can prove not P. For interesting systems, this is what we're talking about. And we also use the term decidability. So we say given a statement P, you can decide that it's true, or you can decide that it's false, or you can decide it's in some set or not in some set. And so, I mean, this was really something we wanted. And what Kurt Gödel did what his proof basically boiled down to was really clever. He showed that when you're talking about numbers, you can use the statements about numbers to make statements about statements. So when I write down a statement, I can actually encode it with a number, right? I mean, you do that when you type things, right? When you're messaging your friends online, you're actually just sending them a string of zeros and ones, right? This is just a number. So Kurt Gödel was, I suppose, one of the first people to realize this. I feel like he was. Certainly people give him a lot of credit for it. So what he did then was he made this really, really clever set of statements, which basically boiled down to him writing the following. G is unprovable. Alright, so this is not actually what he wrote. What he wrote was more along the lines of, he constructed a predicate that given a number, he said this number, or given a number and then another number, he said that the statement or the list of statements corresponding to this first number is not a proof of the statement corresponding to the second number. So basically the first number is not a proof of the second number, where you think the first number is a list of statements and the second number is a statement. And then he showed how to say, well, then we can talk about there exists a proof of this statement or there does not exist a proof of this statement. And then he showed how to get that statement to plug the number into itself, to plug the number corresponding to the statement in as the parameter for the statement. And then he got what basically boils down to this sentence: G, which is the sentence, is unprovable. So this is, of course, the sentence G. Right? So there are some caveats to this that we need to consider. First of all, we're assuming our system is consistent. That is, we're assuming we can't prove that something's true and that it's false, which is a pretty heavy assumption, I guess. I don't know if you guys think consistency, being able to not prove that 1 is equal to 2 is hard to assume. But that's what they assume. And given that assumption, we know that G is a statement without a proof. Why? Because, well, suppose G has a proof. Well, that's really bad. Because you've proven something's true. You've proven that this statement is true, but it says it has no proof, so clearly it's false. And then that would make our system inconsistent. So then the alternative is that it's true, but it has no proof. Right? And of course, maybe you're thinking, well, Dylan, you just gave me a proof. But it's not quite that simple. So yeah, so this was really one of the many genius insights of Kurt Gödel. He actually went on to show that when you talk about systems this strong, not only do you have unprovable statements, but a very important unprovable statement is that the system is consistent. So these systems cannot prove their own consistency, which really hit the final nail in the coffin on Hilbert's dream about mathematics. Kurt Gödel also went on to prove that he proved that the negation of the continuum hypothesis was consistent with the ZFC I was talking about earlier, which, if you don't know what that means, that's okay. He proved something with Einstein once, because he and Einstein were best buds. And it had something to do with like time travel. I think you guys would be much more interested in this than perhaps I would. Or rather, I think you guys are maybe more prepared to understand this than I am. But I think it had to do something with general relativity and like some sort of like a model that fits general relativity that allows for you to somehow spatially go back in time. I don't know. I don't know what this even means. So I'm not a physicist. So yeah.
Something closed time-like curves, something.
Yeah. Closed time-like are two words that I definitely remember hearing in the description of it. So
Are you
yeah.
saying that he proved that there are no closed time-like?
No, he proved that the existence of, I think closed time-like curves is the correct way to refer to these things. He proved that the existence of these things is consistent with Einstein's theory.
Yeah.
So he didn't prove that they exist, but he proved that there is some model of the universe where they exist.
That's the correct.
Yeah.
That's the correct way to say it.
So I think it would probably be much harder to prove that these things exist, especially because they deal with like real things.
It's actually not true.
To prove that they exist.
Well, yeah, I mean, to prove that a closed time-like curve exists.
Okay.
You can just give you can like literally give an explicit example of a pseudo-Riemannian manifold and construct a closed time-like curve. You can literally construct one. It's pretty straightforward.
Do you mean they exist mathematically or in real life?
Oh no, we're talking exist mathematically.
Okay, I was like, what?
I was about to say, you gotta prove some stuff first.
Well, I mean, we don't even know like what our manifold looks like.
Right,
So.
yeah.
I mean, just to be clear, these like any mathematical theory you have about the universe, you don't know if it's true, right?
Mm.
So I don't think we can really prove that they exist without going like experiencing them somehow, measuring them in some way. But even then, that has errors, right? Always. I think I don't know. I don't want to step on like regions that I'm unprepared to talk about while I'm on camera.
There's a reason why most things in physics are theories.
Like gravity.
So yeah, this is really this is like the state of the art on logic that people care about. Up through the 60s, people were concerned about what's provable and what's not. They were concerned about what's computable, so what you can have a computer program to resolve. Maybe you've heard of the halting problem. So given a program, can you algorithmically decide if this program will ever halt? It turns out that this actually boils down to almost the exact same thing, and you can't resolve this, and there's a whole mess of uncomputable problems. And then people just kind of stopped doing it. Now current logic is very esoteric. It's very, very specific problems that people care very little about, except for logicians. But yeah, this is really all you'll ever need to know about logic, other than maybe the basic things that I think I was going to talk about initially, like A and B, and A or B, and A implies B, these sorts of statements to Morgan's laws. But I think if any of you guys want to know about these things, we could talk about it later, or you could look it up, because it's not very hard to find. So yeah, do you guys have any questions about anything? Any more questions? No? Huh?
So I want to have questions, but I don't know enough to ask questions.
So, incidentally, a lot of the people I talked about today, there's like, have any of you guys ever heard of the graphic novel Logic Comics?
Yeah.
It's a very good graphic novel. You should all read it.
We have it in the SPS room.
You guys have it in the SPS room.
Yep.
You should all read it. That was one of the first things that sparked my interest in this sort of stuff. And there's kind of this theme in this book, which I think is historically accurate, that the people that played a big role in this all went insane. Like all of them. And I mean, yeah, I don't feel like Bertrand Russell really went insane. Although that was kind of the theme of the book, was that he was like around all these insane people. But Cantor, he was institutionalized, right? He spent a lot of his time trying to prove something crazy about someone in the Bible, I think. I think something about Jesus having someone as a father. I'm not really sure. It's also not something I really want to talk about on camera.
Dude, Hilbert's kid went insane just by like being near him.
Yeah, I think one of Hilbert's sons ended up committing suicide or something.
Yeah, schizophrenic.
Or yeah, he became schizophrenic. Frege was an anti-Semite. Oh, I didn't even talk about Frege. Oh, that's so sad. Well, there's no point. Wittgenstein was another member of this community. He's a linguistic philosopher that was a student of Bertrand Russell. He apparently asked to be sent to like the front lines when he was drafted.
For inspiration.
Yeah.
And he got it and then left the military.
So yeah, that's maybe a neat fact about these things. I don't know. Maybe that should.
So if you go into math, you'll go crazy? Is that what I got?
No. It's
If you're good at it.
it's only logicians, and unfortunately, all the like really insane things have kind of, all the low hanging insane fruit has been picked. I think to like reap the benefits of, I mean, maybe not benefits, but to get the same outcome that they had, I think you'd have to do a lot more work than they did. Not that this wasn't all brilliant, but we understand it pretty well these days. So yeah.
Thank you.